Hello explorers and welcome to another video. Today I'm gonna talk about machine learning and object detection. This is part 2 in a series, and today we're gonna talk about the configuration, how we can configure our object detection training, so we actually, and evaluation and so on, so we actually get a good model that we can work with. And these kind of parameters can differ on different networks, of course. Today I'm going to talk about the ResNet RCNN version, but there can be differences in the other ones. And one thing that I found when I was researching this is that there isn't actually much information about this. If you search on any of these parameters in this configuration, many times you come to a GitHub question where they tell the user to submit this on Stack Overflow because that is a better place to ask questions. And when you go to that question on Stack Overflow, it's a question without an answer. So I believe that this is something that we really need to get together as a community and actually gather the information, so there is a good way to read about these different parameters, because they can be quite obtuse and they can be hard to understand. And I'm going to give you my collected knowledge about the different parameters, and some of them can be incomplete, and I can also be wrong about some of them, but I believe that I have a pretty good understanding about the different things that goes into this configuration. So let's see here. This is a configuration file. We start off by defining a model, and in this case it's a faster RCNN model. It has a number of classes. In my case with Waldo, where you only have one class, and that's Waldo. And then we have this image resizer, and this is because you want to give the network any image size, but the network can't handle gigantic images because that would require too much memory on the GPU and so on. So you need to downscale it. But I don't want to downscale it too much, so they have actually fixed it in a way that you downscale it to a dimension, and they want to keep the aspect ratio. So they just scale the image down to where you can actually do feature detection but don't have a too large image. So in this case you supply it with a min and max dimension, so they choose a value between that is a good downscale, because sometimes you can't actually just say one specific size, and then you will get some artifacts in the image. So they will find a good downscale that you don't get too many artifacts. And then we have the feature extractor, and that's pretty much the network. So here you can say that I want a faster RCNN REST network, 152 layers. So that's the network I choose. And the first feature, stride, this means where in the image should you find things and how much should you move your window when you're looking for things. And in this case I say that this feature stride should be 16, so it's 16 pixels moving through the image. And that's in the different scaled images as well, because when you go through the convolution you actually have a lot of different sizes downscaled all the way down. So if you have really small objects, you might want to change this value to something lower, just to be able to find these smaller items. So I might try to change these to 8 or 4 with Waldo, because Waldo can be quite small in some images. So I'm thinking about maybe tweaking this value in the future. Then we come to the first stage anchor generator, and this is also something that is really interesting. Here they create a lot of small images in your image where they can find features. So in the different scales, everything from a fourth to a half and the full image, and also the double scale of the image, and also different aspect ratios, they move a window over the image and create different anchor points where they will actually look for your specific object. So this is a generator to create where in the image they should look for objects and how fine-grained this method should be. Next up we have our convolution parameters. So here we set the parameters for each convolution in the layers, and the operation should be convolution. And then we have this L2 regularizor, and from my work with the Java CNN, this L2 regularizor is something where you can give it a little boost in weight to change how easily this model can overfit. So this is one value you can change with a very small increment. So you can give it a weight of 0.0.1 perhaps, if you feel that your network will overfit a lot. So that's one measure you can use to fix your network so it don't overfit. And then we have the initializer, which will use a truncated normal initializer with a standard deviation. And that's because you want to create random numbers in your weights, but to get your training up to running faster, you want it to diverge over the network. So you don't want totally random, you just want it to be pretty much totally random. So this will give you a normalization of all your random weights. So you don't get, for instance, if everything was totally random and you had a value between 0 and 1, then all your values could actually be 1. That's random. But you don't want everything to be 1, because that will not make it a good training set. So this is an attempt to give you something that is similarly random, but still have a diverse group of random numbers. And then we have this set of parameters here that we have a lot of different things going on here. We have the first stage score threshold. So in the first stage of the convolution, which value should I throw away? So if I find an object with a score of, if I set this to 0.1, then everything that is 10% and less will just be thrown away. And also if you look at this intersection over union, so that's how closely you found this object in the image, how good was the match. If that's too bad, you throw that away as well, and that's also a value between 1 and 0. So if you put it at 0, you will keep everything. In my case, I throw away things that don't really fit well, because I don't want to keep all the really bad matches. If you put this to 0, then maybe you will have matches everywhere, and that's not good. You want your bounding boxes to be a little bit better, especially when you in the next stage say how many proposals do I want to save max in the first stage, and in my case I put 100, and if you keep all the bad ones, then you will have 100 bad ones, so that's not good. So these values you can trim to say how much do I want to keep from the first round, and then trim it down to a good set of values that you can work with. And then we have the localization loss weight and objectness loss weight, and this is also similar, but they are looking at the actual loss instead. So here you have a boost in localization and objectness. So how much should the loss be pushed for localization objectness. So in this case, they are more interested in where things are located than what it is. But you can switch these around if you are more interested in knowing what it is than where it is. So that's those values. And then we have the initial crop size. Haven't found anything good to say about this. It's some cropping of the image. You remove some parts of the outer edges of the image, I guess. No documentation whatsoever anywhere. Couldn't find anything in the code, so I'm not really sure what this will entail. Be aware that if you put something very close to the margin of the page and you have a crop size of 14 pixels, maybe you will remove that. That would not be good, because then you will only find things in the middle of the image, perhaps. Max pooling and kernel size and stride. That's when you are shrinking the image. That's how much you want to shrink the image in each layer. So if you have a kernel size of 2 and a stride of 2, you will shrink the image by half, I believe, almost half. So that's what's going on in each max pooling layer. So you have a convolution, max pooling, and then some feature activation, and then you have a convolution, max pooling, feature activation, and so on. So you go around in each layer and having each of these parts in each layer. Then we have the second stage box predictor. So this is when you have ran through all the convolutions, what do you want the last part of this model to be? And in this case, it's a mask RCNN box predictor. And you tell it that it should be a fully connected layer, and you want to keep everything, so you set your dropout keep probability to 1, so keep everything, and use dropout is set to false, so I'm not using a dropout layer at this point. And if I feel that my network overfits too much, it's too good to actually find just the examples given and bad at finding new examples, then it's good to have a dropout layer, set it to 0.9 for instance, so you drop 10% of the values, and then you will get a network that is not overfitted. And also in this fully connected layer, you have this L2 regulator, so you can tweak that weight value as well to also increase the decrease the likelihood that you have a model that will overfit. And then we have the initializer for variance scaling initializer, and that's to figure out how to actually take your features and then upscale them to your image, so you get a good match with the bounding box on the image. And here you say that it should be uniform, and it should be an average between input image and output image. That's pretty much what I can say about this. I don't know how this variance scaling actually works, but I think that these parameters seems reasonable. I don't want it to look only on the input values, and I don't want it only to look at the output values. So an average sounds very reasonable, because you want the bounding box that are close to the object from the input, but also match the actual output of the graph as close as possible. So I don't want to measure one of them over the other. So this is one that was a little bit hard for me to wrap my head around. And then we have the second stage post-processing, and here you actually tell it what you want to keep at the end. So if you what you want to know what you want out from your model and how strict you want to be with your output. So here we have this score threshold again. So if you have objects that isn't sure what it is, then throw them away. And if it's a bad match of the bounding box, throw those away. That's the I over U, intersection over union again. And then we have the maximal detections per class. So if you, let's say, have images with airplanes, bicycles and cars, and you want to find 10 of each maximum, and maximum a total of them. So you could find 10 airplanes, 10 bikes and 10 cars, but you will not find 12 airplanes, for instance. And then we have a score converter. We use softmax, and I think that's reasonable as well. It's very commonly used in convolution and neural network as the last activator for class detection. So that's a good one as well. And then we have this weight again, depending on classification or localization in this stage as well. So you can switch these around depending on what's most important in your network. Then we come to the training configuration, and here we tell it what batch size we want, how much data do we want to read in each iteration. And here we have an optimizer, momentum optimizer, learning rate. So this is just a way for them to encapsulate different things in this configuration, pretty much, because learning rate, that's how fast you want to reach your endpoint, and how little or how much you want to change each time for each iteration. When you find something that is wrong, you want it to push it a little bit in that direction. And then you have a momentum optimizer, and that's a way to speed this process up with a little bit. So if we continue to look here, we have the initial learning rate. So we want it to push it with a 0.001 to start off. So we push it a little bit in that direction, but we have a schedule that says that when we have stepped through more than 900,000 steps, we want to scale this down even more to a 0.00001. And the same goes for 1.2 million steps. We make it even more fine-grained. But we have a momentum optimizer value of 0.9, which I think is pretty much a little bit too much even. So I would scale this momentum down a bit, because I would rather have a model that is well trained than reaching the result fast. Maybe you can skip the momentum optimizer at all. I don't know how this configuration is actually read in the training, if that is possible at all. Then we have this moving average, and that's also an interesting function that I haven't turned on yet. And that is actually a way to cache the result from the last time, and that cached value will slow down your pushing of values. So you will first calculate how much you want to change your weights, and then you average them with the last iteration, so you actually slow down the process and perhaps reach the good medium quicker. So that's an interesting feature. I haven't turned it on, and I don't at the moment don't see any use for it, but if you want to try it out, it's just a flag. And then we have this gradient clipping by norm, and that's a way to make the gradients not overflow over a specific value. So when it comes up to that value, you clip it at that value. So it's pretty much saying that the gradient shouldn't reach over 10. Can't say much about that. The fine-tune checkpoint and from detection checkpoint, these values is if you want to start your model with using an already trained model, but you want to fine-tune it. So you take, for instance, a red inception model, put it into your training, and you need to have the same model set up, of course. And then you take that checkpoint, remove the last layer, so the fully connected layer, and then retrain it to fine-tune and create your own fully connected layer for your specific problem. So that's a very powerful feature that you can use in order to get a good network up and running fast if you are doing feature detections that are very similar to an already trained network. And then we have number of steps, and this is how far this training should run. You can remove this and then it will run indefinitely, so forever. But it could be good to actually set it to a specific number, especially if you are training online. So if you are running it in a big cluster in the compute cloud, it's good to set a number of steps so you know when it should shut down, so you don't just run it without getting that much better result, because this network will give you pretty good results even after 200,000 steps, depending on your input data, of course. How good are your examples and so on. But many of the models that are provided as examples are pretty good after 200 or 500 steps. And then we have this data augmentation option, random horizontal flip. So it's actually, when it's training this network, it's actually flipping the image in a horizontal way back and forth in order to make it more robust against different orientations of the image. No, not orientations, but you know what I mean, different sides. So if you see a dog standing looking to the left, it should not be only finding left wards looking dogs, it should be also finding rightwards looking dogs, so on. So that's an interesting feature, to actually flip the image from each training. And then we have the train input reader. It's pretty self-explanatory. You have a TF record input reader where you set the path of your TF records file. So from where should it read your examples. Then we have a label map data file, and this is where you have all your different labels. So for instance, in my case I have Waldo, so that's one label, and we will look at the label file later. So it's pretty simple file. And then if you want, you can shuffle the input and how many readers you should use to read the records. So that's how many threads should actually read the data. And that's because if you have a very fast GPU, you might want to spend more time with different CPUs to read your data from disk, so you can actually provide enough data for your GPUs to be fully efficient. And then we have the eval configuration. How many examples do you want to evaluate, and how many times do you want to evaluate them? Also very self-explanatory configuration. And then we have a similar reader for the eval. So here you supply the TF records that you want to evaluate with, and also the label file for those. And if you want to shuffle, and how many readers. And lastly, the label file, and this is my label file. It's one item, so it's only one label. It has an ID of 1, so that's the actual label value saved in your records examples. And then we have a name for that label. So this is what I wanted to go through today. As you might have understand, everything in this this video is not facts. It's my understanding of the configuration file. I hope that you find these files a little bit more readable by now. I hope that you understand this process a little bit more. I hope that you learned something today. If you have any questions, suggestions, or thoughts, leave them in the comment section below. If you like this video, give it a like, share it with your friends and colleagues. If you haven't subscribed yet and want to follow along in this series, please subscribe. And I really hope to see you in the next video.